Sketch the following spectra that would be obtained for 2-chloroethanol. Let's first draw the structure of 2-chloroethanol. Okay, here we have 2-chloroethanol. And the first one is draw the H&MR spectrum for an anhydrous sample of the alcohol. So this is basically pure alcohol which doesn't have any water. So when there is no water, then there is not going to be any proton exchange. So there is no proton exchange. So which means this hydrogen that is attached to oxygen that is present in the alcohol hydroxy group is definitely going to be there all the time. So these hydrogens are going to experience the effect of this hydrogen, magnetic moment of this hydrogen. So let's find out, let's first label the hydrogens. So this is going to be A, this is B, this is C. So A is going to be split as a triplet because we do have 2 protons here. So 2 plus 1, that should be split as a triplet. And B should be experiencing the effect of hydrogens of the hydroxy group and as well as these methylene protons. So this is where we have to use the Na plus 1 times Nb plus 1 formula. Okay. So we have 2 hydrogens here. So it's going to be 2 plus 1 times 1 hydrogen right there. So it's going to be 1 plus 1. So basically this is going to be 3 times 2. That would be totally 6 peaks. It will be split as 6 peaks. And then let's go on to C. C has got totally 2 neighboring hydrogens. So this should be split as a triplet also. Let's draw the H&MR spectrum of this compound. The OH peak can come anywhere, but it's going to be split as a triplet. So let's draw the triplet here. And it's going to correspond for 1 hydrogen, right? And then we have 2 CH2s. One CH2 is closer to Cl, and the other one is closer to oxygen. Which of this is going to come in downfield region? Obviously, this CH2 because chlorine is more electronegative. And again, this again is going to split as a triplet. And then these hydrogens is going to be split as a sextet, which is going to look like this. So this should be the H&MR spectrum of the compound in the anhydrous state. The next part of this question is where we have to draw the H&MR spectrum for a sample of the alcohol that contains trace amount of acid. When you have trace amount of acid present in the solution, what could happen is there could be proton exchange. Proton exchange between the hydrogen that is attached to the oxygen and the hydrogen that is present in the acid, right? So because of which these hydrogens are not going to see the effect of the magnetic moment of this hydrogen. So therefore, these hydrogens are going to have only 2 neighboring protons, which is going to make them split as a triplet. So these hydrogens are going to be split as a triplet, and in the same way, these hydrogens are going to experience the effect of only these 2 hydrogens, and therefore they should also be split as a triplet. So there will be 2 triplets here. And also there will be 1 singlet. Probably this will be slightly broad, and that's going to correspond for the OH group. So this is going to be the H&MR spectrum for the sample of the alcohol when there is little amount of acid present. Let's go on to the next one, the C13 NMR spectrum for this compound. There are only 2 carbons here, and consider this as a decoupled, proton decoupled spectrum. So if it's going to be a proton decoupled spectrum, then these carbons are not going to experience the effect of these hydrogens. So there should be 2 singlets. That's it. Let's go on to the proton coupled C13. So this is where the carbons are going to experience the effect of the hydrogens that it is attached to. So Cl, CH2, CH2, OH. So when I consider this carbon has got 2 neighboring protons. So therefore, this is where the splitting comes. So remember, only in the proton coupled C13 you will be seeing splitting patterns. So this is going to be split as a triplet, And this is again going to be this carbon right here. Carbon signal is going to be split as a triplet again. So you will again see two triplets, one for this and one for this carbon. And those are the only two carbons that is present, so you will only see two signals. Let's go on to the last part. The last part is where we have to draw the four parts of the DEPT-13 NMR spectrum. Now, what is DEPT-13 NMR spectrum? DEPT-13, the expansion for DEPT is distortionless enhancement by polarization transfer. That's the expansion for DEPT. Now, using a DEPT will help us to identify the different types of carbon. Say, for example, quaternary carbons, methane carbons, methylene carbons, and methyl carbons can be easily identified using DEPT-13. Okay. Now, for example, when you take DEPT-45, this is not going to show the quaternary carbons, so no quaternary carbons. And let's say that if you're going to do a DEPT-90, this is only going to show the methane carbons. So something which is going to be like this. And then when you do DEPT-135, some interesting thing happens here. It will show the methane carbon signal in the upward direction, and as well as the methyl carbon signal in the upward direction, whereas the methylene carbon signals will be in the downward direction. Okay, so let's draw the four parts of this in a DEPT-13. Let's start with all carbons. There are only two carbons here. Let's draw the structure here. We only have two carbons here, and that to two methylene carbons. So you will only see two peaks when you have the all C13. When you do DEPT-45, that's going to show only, that's going to leave the quaternary carbons. Anyways, we don't have any quaternary carbons. You're still going to see two signals for the DEPT in the DEPT-45. And then when you do DEPT-90, that's going to show only the methane carbons. We don't have any methane carbons, so that will be blank. There will not be any signals here. Let's do the 135, DEPT-135. The 135 is going to make the methylene carbon signal shift downward. Okay, so this is what you'll be getting. Okay, so here is all the four parts of the DEPT-13 NMR spectrum.